Go ahead, Chris.
Great, thanks. I assume everyone can hear me properly and hopefully see my mouse. I'll be talking about yield modeling, how that allows us to optimize a survey, and how those two concepts together can let us help us design a mission like the Habitable Worlds Observatory. I'd like to start off with a bit of a historical perspective, which is that exoplanet yield modeling was really born out of TPF. And in my mind, the single most important foundational paper of this field was written by Bob Brown in 2005, and he titled it Single Visit Photometric and Obscurational Completeness. There's a lot in that title. Let me sort of break it down. What Bob was modeling was basically the fact that when you observe a planetary system with your coronagraph, some of the planets in that system will be obscured, okay? And other planets will be too faint to detect, hence the term photometric. But we can predict which planets we would have detected and calculate the probability that we would have seen them. And that is this term completeness, which I'll get to a little bit later. There is a lot in this paper, and if you're interested in getting into the field of yields, if you will, then I suggest starting with this paper. He produced this bird diagram, which is shown on the lower left. I'll discuss that later. You'll be working with that during this afternoon's hands-on session, and it allows you to calculate this quantity called completeness. And he even introduced the idea of survey optimization back in this paper. So a fantastic starting point. I want to emphasize that exoplanet yields were born out of TPF out of necessity, okay? We haven't seen a lot of yield calculations for galaxies or anything like that. Why is that? Why is the field of direct imaging of exoplanets so focused on yield? Well, at the most fundamental level, our ability really to learn about anything in the universe is founded on sample size, right? Can we understand stellar evolution by just studying the sun? Obviously not. And this is true with exoplanets as well. And so to understand any single exo-Earth candidate, we're going to have, some collection of its peers to study it. But even to understand exo-Earth in general, we are going to need a larger sample of other types of exoplanets as well. But maybe the primary reason why why yield calculation was really developed is because it helps us make sense of a very complicated multivariate trade space. So as it turns out, coronagraph design itself is multivariate. We just heard about this and the idea that there's no free lunch. You're always trading one parameter for another. And a chronograph's performance is not just about contrast and inner working angle. It depends upon throughput. It depends upon outer working angle, bandwidth, sensitivity to low order aberrations. And so inherently, these instruments are very complicated, and it was difficult to understand how that translated to astronomy, right? But it turns out that the astronomy side is also complicated because the scale of a habitable zone changes with spectral type and distance to the star, and the contrast of an Earth twin changes with spectral type. So getting these two complicated things to map together was totally non-intuitive, and that's why we have yield calculations. They do that for us. One of the really great aspects of yield calculations is it goes beyond capability, and it really relates scientific productivity to mission design. So we can now relate, these sort of bulk mission parameters to our ability to really conduct a full survey if we want. And one of the things where yield calculations have really excelled, maybe unexpectedly, is that they have provided a lot of lessons about how we should actually operate our mission and how we should conduct the survey. I think some of us didn't really see this coming, but we've learned a lot from them, and I'll touch on some of those lessons learned in the last half of this talk. So before I get to how we perform yield calculations, I'd first like to back up and just ask the question, how do you pick a yield goal, right? Are we after 1 planet, 10 planets, 1,000 planets? How do you make that determination? And I made a suggestion for this back in 2014, which is to just start with, a basic fundamental statistical argument based upon the binomial function, which I show in the top left. And this binomial function expresses the probability of X successes out of N tries, where each individual try has a probability of success lowercase p. If instead of talking about N tries, we're talking about N exo-Earth candidates, and instead of the probability of success being, we're going to substitute for that. We're going to substitute maybe anything we want to learn about an exoearth candidate. Let it be, let's say, the fraction of them that have life, remotely detectable life. Then we can substitute those values into that equation and rearrange it to the equation shown on the lower left. And what that equation on the lower left says is the number of exoearth candidates that you need to have a given confidence C in finding at least one that has remotely detectable life. That equation is plotted in the right. So, for example, if we were to survey a dozen exoearth candidates on the y-axis, and F sub life was 10%, then we'd have roughly a 68% chance of finding at least one that has remotely detectable life. If we wanted to increase our confidence to 95%, we'd have to survey on the order of 30 exoearth candidates. So this does not tell you what your yield goal is, but it's a really nice statistical structure that allows you to at least understand the gamble that you are making with the universe. What I think is more impactful, actually, is the statistical structure that underlies this plot is the same as what tells you about what happens if you have a null result. So we can actually just retitle this plot to the exoearth candidate yield required to constrain F sub life in the event of a null result. So in other words, if we survey 30 exoearth candidates and none of them show signs of life, then we can say with 95% confidence that F sub life must be less than 10%. This is extremely powerful. We're no longer talking about just designing a mission to get lucky. We're talking about designing a proper physics experiment that will quantitatively address how alone we are, regardless of the outcome. And I think this is probably what motivated, at some level, the recommendation of the ASTRO 2020 Decadal Survey. So once we have a yield goal in mind, we can set forth and actually estimate what a survey-long mission yield for, let's say, exoearth candidates would be for something like HWO. So how do we do that? Well, at the most fundamental level, what we're essentially doing is playing make-believe, right? So we're simulating a blind survey of stars, searching for exoearth candidates that we don't know if they're there or not. And to do that, we take known nearby stars in the night sky. You can see most of these with your naked eye. And we distribute fictitious planets around them and fictitious debris disks. And we simulate the response of a chronograph and ask, could we detect that planet or not? And maybe a code like ExoSims would do this 1,000 times and calculate what fraction of the time we get a given yield goal, for example. Now, as you can imagine, doing this requires a very long list of inputs. So we have astrophysical assumptions that describe the universe as we know it. What stars could you survey? What is the brightness of exozodi? What are the occurrence rates of these planets? Which, if you're talking about exoearth candidates, we're talking about Eta Earth then. What are the observational requirements? If we want to see a given molecular species in the atmosphere of these planets, what wavelength and SNR do we need to do that? And then we have a technical description of the mission, including both the telescope and the instrument. Things like what is our contrast? What are the overheads? What are the slew times? All of those things get put into a yield calculator, and then it simulates end-to-end a survey. Now, there are two major components of all yield calculators. The first is something called a completeness calculator. And this is really, what is the benefit of making an observation? What are the chances that we are going to detect a planet? But we also want to know what the cost is of making that observation. And so we need an exposure time calculator for yield calculations. These are the two major components in every yield calculator. I'll talk about each of these here in a minute. Some yield calculators also have a third component, which is basically examining the feasibility of performing a given observation. In other words, scheduling the observation and is that target actually available when you want it to be available. You will work on that aspect this afternoon in the hands-on session, but I'm going to limit the conversation here to just these two. So first, let's talk about completeness calculation. What is it? Why are we calculating it? Bob Brown introduced this concept in 2004, and completeness he defined as the chance of observing a given planet around a given star if that planet exists. And to calculate this, what Bob did was distribute a very large number of synthetic exoplanets, let's say exo-Earths, sampling all possible orbits in the habitable zone of a given star. And he distributed maybe 10 to the fifth, 10 to the sixth of these, sampled all possible orbits, radii, phases, illuminated them all with starlight. And then for each of those, he calculated the projected separation from the vantage point of the telescope and the delta mag of that planet, or in other words, the contrast. And if you do this enough times, maybe 1,000,000 times, you can build up a probability distribution function for those exo-Earths. And you can plot that in terms of apparent separation and delta magnitude. And you get something that looks like this bird diagram that he showed. So you can see that for randomly distributed exo-Earths that have a range of possible orbits, your highest probability of finding them is down in this region of phase space. I'm assuming you can see my cursor. And what Bob showed is that you can apply a toy model of a coronagraph to this diagram to then calculate the chance of finding one of these planets if it exists. So for example, our toy model of a coronagraph might have a projected inner working angle, like the red line shown here, and so you can't see planets to the left of that. And it might have a projected outer working angle like this line shown here, and any of the planets in between there are fair game for observation. But you don't get to observe all of those because, we're not necessarily going to observe to a delta mag of 32. And so there's another cut that gets applied in here based upon our observation depth that we choose based upon exposure time. And so if these are the toy model cuts of our coronagraph, then the phase space that remains at the bottom, we can simply add up the density distribution in there, and the completeness is that fraction of the PDF. So let's say 50% of the PDF is in that box, then our completeness would be 50%, and the yield of this observation would then be completeness times eta Earth. So this is how Bob presented it initially. I want to make a couple of notes about it. When we treat completeness here in separation and delta mag space, there's a few things to keep in mind. I showed you sort of a toy model of a coronagraph. A realistic coronagraph performance would have a much more complex behavior of observation depth as a function of separation. So instead of being a top hat function, it might be a bit of a wiggly line with some slope to it. This also assumes a radial performance for your coronagraph, when in reality, some coronagraphs have a two-dimensional, speckle pattern or a two-dimensional even throughput pattern. And if we wanted to apply a realistic coronagraph to this, that means we'd have to be able to figure out what that observation depth is as a function of separation. And that means translating exposure time into an observation depth here. So I'm going to show you an alternate approach to thinking about completeness. This approach here with the bird diagram, this is something that you'll be working on in this afternoon's session, applying cuts like this and calculating completeness. An alternative to that is thinking basically collapsing separation and delta mag into one parameter, which is exposure time. And so if we take our synthetic cloud of exo-Earths, instead of calculating separation delta mag, we actually calculate the exposure time for every single exo-Earth in here, then we're going to find that some of those are nearly impossible to observe because they're in the inner working angle of the coronagraph. Another fraction of those are in crescent phase from our vantage point and simply too faint to observe within a reasonable exposure time, tau. And the fraction that remains is the completeness. So again, we won't touch on this in the afternoon session, but this is an alternative way to approach the problem. Another thing that you won't touch on this afternoon, but is a very important concept to keep in mind, is the idea of revisit completeness. So far I've described what completeness is for the first time you observe a system. But of course, after our first observation, we could wait 6 months, come along, revisit that system. The planets would have orbited around the star, and we could now be sensitive to planets that previously we were not able to observe. So most modern yield calculators have some form of revisit completeness calculator in them, and this is a very important, albeit complicated part of yield calculations. The next topic I'd like to talk about is the second major component of all yield calculators, which is the exposure time calculation. And so I'll walk you through how most yield calculators approach exposure time calculations. Typically, we are assuming aperture photometry, and we're assuming the ability to empirically or via a model subtract all background sources. I'm going to start off by assuming that we can subtract everything down to the Poisson noise limit, because the Poisson noise limit has this very nice analytic relationship in that the Poisson noise contributed by anything, if you can subtract it, is the square root of the expected counts. So taking the image on the left, let's say we wanted to calculate the exposure time of the planet in the upper right. We'd put our photometric aperture in our image, and we could just state that our signal is therefore the total of all of the planet's counts that are within that photometric aperture over some exposure time tau. And the noise in that photometric aperture is, assuming Poisson noise, is the square root of the total counts in that photometric aperture. Now, you can argue about whether the planet should be included in that total counts or not, and it depends on what you're after. I won't get into that too much. But we can take the language that I've printed down here in the bottom part of this slide and translate that into a mathematical expression for signal to noise. It's simply the ratio of the total planet counts, or the count rate of the planet times the exposure time, over the square root of the total counts. And I've broken the total counts down into count rate of the planet and the count rate of all other background sources. We can then rearrange that, solve for exposure time for a given SNR, and you arrive at the sort of most fundamental form of a coronagraph's exposure time equation. It can get a lot more complicated than this, but this is the basic form of that exposure time equation. I'll give you some insight into how things might change depending on different assumptions. So for example, if we wanted to include a systematic noise floor, in other words, you can subtract down to the Poisson noise floor as long as the Poisson noise floor is higher than some instrumental limit, then you get this additional term in the denominator. This term in the denominator represents our noise floor, and it basically ensures that the exposure time balloons to infinity as we approach it. I've also put a factor of 2 here on our background count rates. This comes from an assumption basically about PSF subtraction. If you're performing angular differential imaging, you would need to carry a factor of 2. Because it's empirical, it basically doubles the count rate of all background sources. If you had a model-based PSF subtraction, then you'd have a factor of 1 there. And in this afternoon's hands-on session, you will have both the noise floor term, and I don't think you'll have the factor of 2 here, but just be aware that the exposure time equation varies from model to model and from user to user. Let's talk about the different types of background sources that go into the Poisson noise calculated for an exposure time. There are many potential sources of background for a chronographic observation. I'm just highlighting the 4 main sources that we usually worry about. The first is unsuppressed starlight. So the chronograph is only going to perform so well. And even in the dark zone that, it achieves 10 to the -10 contrast, we still have residual speckles that we have to worry about in there that are going to contribute shot noise, even if we can subtract them perfectly. We know our astrophysical scene will have exozodiacal light. We know that there will be dust in these systems scattering light toward us, and its distribution is going to be a very complicated function of many different things. We will have local zodiacal light. Basically, we have dust in the solar system that we have to look through to see these other planetary systems. But the field of view of our instrument is so small that to first order, it's just going to look like a uniform flux. There might be a slight gradient to it. And then the detector noise is to first order either going to be a uniform or a gradient as well that you can then take the square root of to approximate as Poisson noise. I've broken down the equations into each of the contributions. So I have the count rate of the planet up here and analytic expressions for those 4 main sources. I'm not going to go in this at all. If you're interested, this is here for your reference, and you can refer to my 2014 and 2015 paper, or a lot of Dimitri's and Rhonda's papers as well, to understand this in more detail. But there are existing exposure time calculators out there. So ExoSIMS is publicly available. This is the yield code that Dimitri invented, and Rhonda has contributed a lot to. It is 100%, I believe, in Python. ExoSIMS is more than just an exposure time calculator. It is the whole kit and caboodle. So it calculates yields, it calculates completeness, scheduler, it has a scheduler in it. And it is the tool that you'll be using this afternoon during the hands-on session. There is another tool called EBS, and it is basically a wrapper around ExoSIMS so that it is mostly geared towards just calculating exposure times, not calculating yields. This was invented by Pen Chen and Sarah Steiger. It is also 100% Python and available on GitHub. And then just recently, I put up the exposure time calculator that I use inside my yield code called the Altruistic Yield Optimizer. It is in IDL and C, and we are working on translating that to Python and C, and it should be there soon. I want to quickly note that all three of these ETCs have been cross-model validated. This was part of the START and TAG efforts, and to the extent possible, they all agree. But we have found that in spite of all agreeing, we still sometimes have differences, and oftentimes that is due to differences in assumptions or user error. So these are quite complicated to use, and I'll touch on that in the lessons learned. All right, so we have a completeness calculator, we have an exposure time calculator. How do we combine those to simulate a survey? And moreover, how do we optimize observations using those? So as a reminder, completeness tells us what the yield will be. It's the bang that you get for your buck, and the buck is the exposure time. So one thing to keep in mind is on this diagram I showed you previously, completeness in this illustration is obviously a function of exposure time, right? And so the completeness you get during an observation depends on your choice of exposure time. How do you choose an exposure time? Well, if you plot completeness as a function of exposure time, it typically looks something like this black solid line. And the derivative of this curve tells you the incremental bang for your buck that you get if you invest a little bit of time in that observation. So what some yield calculators will do is calculate the derivative of completeness as a function of time, and that tells us which observations are the most deserving to invest exposure time in. We can also then calculate the completeness over exposure time, the ratio of completeness over exposure time, to determine the maximally productive stars at the end of this process. So we can optimize both the stars that are selected for observation and the exposure times of each individual observation through curves like this. And this process can potentially double yield from the past. I won't go too much into the details of optimization. I'll simply point out some of the advances that have been made. So optimization has been part of yield calculations since the very beginning with Bob Brown's paper, where he's using basically toy parameters to try to improve the yield of the mission. One of the most important papers in all of the optimization work that's been done was written by Sarah Hunyadi. It was a relatively unknown paper for quite a few years after it was written back in 2007. But is foundational. And basically, she showed that if your observations are optimized properly, that means the derivative of all completeness curves with respect to exposure time should be the same, evaluated at the exposure time of that observation. And this has been fed forward into many yield codes now. Dimitri and Jeremy Kasdan did a lot of work on a different type of optimization, looking at how coronagraphs and star shades play together, and showed that, you probably want to use them in different ways, because when you try to use them to amplify each other's contrast, it doesn't work so well. So they looked at a lot of situations with hybrid missions. I came on the scene in 2014, accidentally reinvented Sarah Hunyadi's method for optimization, which back then was for single visit only, and then I extended that to multi-visit completeness. Rhonda Morgan in 2021 has been, in addition to that paper, has been looking a lot at optimization based upon precursor information. So she's showing that if you have, let's say, EPRV priors, you can take advantage of those and achieve faster yields. And then just recently this year, I published a paper showing that we can now optimize what wavelength or bandpass every observation should be to maximize the yield of a mission. This is probably a good point to mention that there are two different types of yield calculators out there. There are summed completeness yield calculators, which is like AYO, the code that I use. And there are mission Monte Carlo simulations, which is like ExoSims, which we'll be using this afternoon. And a summed completeness calculator is a little more straightforward, that it is what it says. In other words, you're basically summing up the completeness of every observation and calculating a yield that way. This is relatively straightforward to compute, and it allows for easier optimization of the observations. The problem is that it ignores schedulability altogether at this point in time, and yield uncertainties are a bit harder to estimate because it is inherently returning the expectation value of the yield only. Mission Monte Carlo simulations, on the other hand, like ExoSims, it will actually schedule individual observations and integrate the orbit of the spacecraft and determine whether things are, within your field of regard. And it will do this maybe 1,000 times for different incarnations of the universe, and therefore automatically include some aspects of uncertainty in it. The problem is that this tends to be more computationally costly, and you have to include some form of decision-making strategy. So if your decision-making strategy is non-optimal, that means that your yields will be non-optimal. And this is kind of a murky area that we're still learning about. So both of these methods are independent. They are very complementary. They both have their strengths and weaknesses. But they're both converging. So the cons for the summed completeness method are actively being worked, and some have been largely overcome. And the same is true for the Mission Monte Carlo simulation. So Dimitri has worked a lot on reducing computational cost. You'll be able to use one of these this afternoon very easily. And they're making some progress on their decision-making strategy and optimizing observations as well. So hopefully in the next few years, the yields estimated by these methods really converge to an even greater degree than they are right now. So I think I have about 15 minutes left, and I'd like to spend the rest of this time discussing what we have learned from yield calculations. One of the main things we have learned is that yield is most sensitive to aperture size. So we started turning knobs on our mission model and calculating how yield responded to changes in individual mission parameters. I'm showing you some of those sensitivity curves here, and the value of phi in the upper left-hand corner tells you the power law relationship between yield and a change in that single parameter. And as you can see, yield is most sensitive to the telescope diameter. It is still strongly sensitive to the inner working angle of the chronograph. It roughly goes as 1 over the inner working angle. It is moderately sensitive to things like throughput and bandwidth and survey time. And it is relatively weakly dependent upon raw contrast, at least down at the 10 to the negative 10 level, as well as a few other things. You'll notice that one of these curves does not look like the other. You'll see this plot on the lower left called limiting magnitude. That's basically the noise floor. And you can see that you can very easily fall off a cliff for that parameter. So that is something that we need to make sure that we watch that and we hit the noise floor that we need for when designing HWO. Another thing we learned is that all of these parameters are correlated. All of the sensitivities are correlated. And so there have been a number of studies showing this. Here's an example by Rhonda Morgan, where she showed that the inner working angle and the contrast joint sensitivity depends on things like wavelength and telescope diameter. And it probably also depends, on outer working angle and things like that. So if you change any one parameter and put your mission in a different point of phase space, the sensitivities will change, right? So if I radically improve throughput, then my sensitivity to throughput usually goes down and sensitivity to other things usually goes up. So this is really important to keep in mind. Extrapolation with any, with multiple parameters is usually potentially a dangerous thing to do. I wanted to talk about real quickly why yield is most sensitive to aperture size and why we made the statement years ago that yield is controlled the first order by aperture size. And it's basically because you get 3 things for the price of 1. First, you get a larger photon bucket. So you simply are collecting more photons per unit time. That's pretty obvious. But you also get a sharper PSF. And many of these targets are going to be in the background limited regime, probably due to exozody. So I'm showing you here a 4-meter telescope's observation of a planetary system. There's a planet on the left. It's embedded within a bright exozodiacal disk. And if we were to instead observe the system with a 12-meter telescope, albeit the chronograph changes a little bit here, but you can see that the point source jumps out immediately. You are basically able to resolve out the exozodi. And these two things together means that exposure times in the background limited regime go roughly as d to the negative 4. It's actually faster than that for some chronographs like d to the negative 5. I won't get into why that is. But the other thing that you get with a larger telescope is you get a smaller inner working angle. So if we grow our telescope here, then the inner working angle shrinks, and we can see targets that are at larger distances. This basically means that our target list can grow. So all three things together contribute to that, roughly equally to that very high sensitivity with telescope diameter. Moving on, other lessons we have learned is that we can use astronomical and observational degrees of freedom to our advantage when designing the mission. So here are a couple of examples of that. On the left, I'm showing you that yield codes can pick out which stars are most productive. So we can use that ratio of completeness over exposure time to choose the most productive stars. And for different chronographs, you might get very different target lists. I'm plotting here, these are scatter plots of luminosity versus distance for the stars that AYO selects for two different chronograph designs. You can see they are completely different target lists. And if, for example, we had come and said, well, we need to observe G stars at 10 parsecs, our mission must observe G stars at 10 parsecs, that would have been a really bad choice for both of these chronographs. And their yield would have looked like it was 0. And so we want to make sure that our target lists are being informed by yield calculations, and we're always playing to the strengths of the mission. Otherwise, we could get incorrect trade studies. On the right is an example where we can adapt the observations to emission strength. So here I'm not talking about which stars we observe, but how we observe them. And so this plot on the right is color-coded by detection wavelength. AYO will optimize what the bandpass is for detection of these planets. And usually these dots all look sort of purplish, right? So it usually picks about 500 nanometers for most targets. But you can see that a very large fraction of this list for this 400 channel PIC chronograph is red. And that means it's choosing to observe them at the longest wavelength, 1 micron, which is very counterintuitive because this means our inner working angle is worse. It means there's more exozodi in the signal. It means generally some of these stars are a bit fainter. Why on earth would it be doing this? As it turns out, this coronagraph is very sensitive to stellar diameter. And so if for a perfect point source, 0 stellar diameter, this coronagraph might have a fantastic contrast, maybe 10 to the negative 14 on paper. But for a finite stellar diameter, its contrast can degrade all the way to 10 to the negative 8, something that is actually prohibitive. So what the yield code is doing is it is choosing to work at a longer wavelength where the star appears smaller in units of lambda over d. And that it improves the contrast of the observation, and you're buying down some of the weaknesses of that chronograph's sensitivity to stellar diameter. We see this again and again. We've looked at even assigning chronograph masks on a star-by-star basis. So we now know that we can design suites of chronographs that are designed to play together well. One chronograph does not have to do everything. We can optimally assign chronographs on a star-by-star basis and design a suite that works together very well. One appealing aspect of this is this potentially helps relax chronograph design trade space because, as the previous talk just mentioned, when you design an instrument, there is no free lunch. And if you want improved contrast, sometimes you have to give up inner working angle or a throughput for that. So by taking advantage of astronomical degrees of freedom and splitting up the chronograph design based upon those, you might be able to gain back some of that performance. Another lesson that yield codes taught us, shockingly, like 8 or 9 years ago, was that operating inside of the inner working angle is potentially very productive. And so I didn't catch all of the talks in the workshop here, but some of you may have heard that the inner working angle is a region interior to which you can't detect planets. And that's not true. It's a bit of a misnomer. The inner working angle is simply a mathematical description of the chronograph. And so to illustrate that, I'm showing you in this plot here, the performance of a DM-assisted vortex chronograph. And the black solid line is the core throughput of the off-axis PSF. Basically, this is the throughput of the planet as a function of stellocentric separation. The inner working angle for this chronograph is simply defined as the separation at which it falls to 50% of its max. So you can see its max is roughly 45%, and so the inner working angle would be somewhere around 3.5 lambda over d here. But there's nothing stopping us from working at 3 lambda over d. There's still useful throughput here, 2 lambda over d. Even 1.5 lambda over d, there is still useful throughput there, as long as we can deal with the degraded contrast at those separations, and as long as we can deal with the fact that we have barely resolved our planetary system at those separations, there's no reason why we can't do this. And in fact, JWST has already done this. So just recently, it detected, first of all, we were seeing this in yield calculations almost a decade ago, and kind of wondering whether this was possible. And just recently, JWST has shown that it detected planets at 1.8 lambda over d using a chronograph that was originally designed with an inner working angle of 6 lambda over d. So again, yield codes are telling us potentially about how to conduct these observations. They have also taught us that precursor information is potentially valuable. So on the left here is a study from Rhonda Morgan where she showed that by having EPRV knowledge going into a blind survey, you can not only achieve faster ExoEarth candidate yields, which is important actually because it helps buy down risk for the mission, allows us to complete our science earlier on in the mission lifetime, but potentially you can even get slightly higher yields depending on how much of that precursor knowledge you have. And Corey Spohn recently showed that your ability to use this precursor information really depends upon, in large part, on the field of regard. So if you have if you only get to see a very small strip of the sky smaller than what JWST sees, let's say 10 degrees total, which would be the lower left-hand corner of the plot, you're only going to see about 60% of the EPRV detected ExoEarth candidates than if you had a much larger field of regard. So field of regard, your ability to pitch toward the sun and away from the sun is a very important aspect of this mission. We have learned that star shades and chronographs are very complementary and should be operated differently. So Dimitri and Jeremy started looking at this back in 2008. The HabEx mission concept looked at this again and found out, basically decided that chronographs are really good at detections and star shades are really good at characterizations. And if you use them in that way, then a hybrid mission can get you most of what you want with a smaller telescope diameter. We have learned that the metric that we use to define yield is very important. So you will hear many people, myself included, sort of recklessly say, oh, the yield of a mission is, XYZ, without defining what that means necessarily. And so it's very important that we understand the assumptions that go into these things. And so Rhonda has been showing this. Here's a plot from her from a talk she gave in 2022, where she showed that, if your yield metric is complete, quote unquote, characterization of an ExoEarth all the way from the UV to the near infrared, this is going to take a long time to do. And we're not going to be able to do this probably on every single planet. If, on the other hand, all you do is search for water vapor, right, you're going to get a very small snippet of the spectrum. And so obviously one looks much better than the other, but the one on the top, you're going to get to do, your yield for that would be much lower. So these are sort of apple and oranges comparison, and we need to be very careful about what we want on every planet versus what we can get on a subset of the planets. And then there was a paper recently by Noah Tusha where he showed for the first time that a mission that is designed to image or characterize ExoEarths, turns out that that is going to absolutely excel at detecting cool Jupiters. And so as you can imagine, if your goal is to image Jupiters, you could survey many more stars. He showed you could survey more than 1,000 stars in just 6 months' time, if that is your metric. And shockingly, all of the exposure times of all of these stars are dominated by SLUs. So this really points to the fact that if we want to think about, we need to think about these other metrics when designing the system to make sure we're not creating a system that makes it difficult to accomplish other science. Another major lesson is that uncertainties matter in yields a lot. Yields are inherently very uncertain. Dimitri has been showing this since 2016 with his Monte Carlo mission simulation, showing that yield is not just a single number, it is a distribution, and we might get lucky with yield, we might get unlucky. I recently just put a paper on arXiv that tried to break down how every major source of astrophysical uncertainty would impact the yield. And we showed that uncertainty in Eta Earth is by far the dominant source. But surprisingly, there is a second dominant source that we basically can't retire before the mission is designed, which is inherent to a blind survey. It's just Poisson statistics of which stars the planets are around. In that same paper, we showed a lesson that quite honestly kind of contradicted something that I've shown in the past. So I previously said that yield is most sensitive to aperture size, which is correct. And therefore that to first order yield is controlled by aperture size. And I think that's largely true, but something that we didn't appreciate at that time is that, when you talk about yield being controlled by aperture size, there's really only one knob that changes your aperture size, and that's the size of the aperture, right? But when you talk about all these other parameters that yield is only moderately sensitive to, like throughput and bandwidth, turns out there's dozens of knobs that you can turn. And if you turn them, the yield is actually compiles. So you can actually potentially more than triple your yield by turning a lot of these knobs all in the same direction. So we've learned now that many small changes can compile to produce very big differences in yield. Another lesson learned is something that Dimitri sent to me in an email recently, and I loved his quote so much I just put it on the slide, which is to beware of yield erosion, because every bit of added fidelity in our simulations to date tends to decrease the projected yield. So this is something we should think about budgeting for when designing a future mission. And maybe the last lesson, this probably comes across as flippant, but yield is hard. And I think anybody that is in the field of yield calculation, and certainly anybody that participated in the ETC cross-model validation, appreciates this, because coronagraph exposure time calculations are very detail-oriented. It's a very tedious thing. Completeness calculation is very tedious. And certainly survey simulation with all of these inputs is very tedious, and there's lots of opportunities for error. And even people that have been doing this, for over a decade, we still run into those issues of user error here and there. So cross-model validation is very important, as are things like output visualizations, which let us check the results and make sure we understand sort of the choices that yield calculations are making. And with that, I will end and take any questions.
Hey, thank you, Chris. I'm afraid we only have time for one question. Any online that you want to do? Let's take one from online. Okay, Chris, considering you want to look for disequilibrium chemistry in every habitable world, what band of observation yields the maximum for HWO? Has the community looked into it?
Yeah, that's a great question. So we're still trying to get clear guidance on sort of what the minimum observational criteria is on every XWORTH candidate. During the LUVOIR and HABEX studies, the teams kind of settled on, well, we want to detect them, we want to measure their orbits, and we want to search for water vapor. And once you've done that, we see that as sort of the entry point for future characterization on those planets. But we wanted to benchmark a mission that could do those things. So it's sort of up to start at this point to come up with some ideas on what those metrics might look like, and then eventually up to the project office to really make a decision about what is the minimum science that we want to do and how many times do we need to do it, and what is consistent with the recommendations of the decadal.
Okay.
But as I mentioned, the more stringent that metric is, the lower your yields are going to be. So if you want oxygen and water vapor and carbon dioxide on every planet, well, that's going to drive mission yields much lower. And if you're still trying to hit the same number, then that's going to drive the cost of the mission through the roof. So we need to be cognizant both of reality and ambition.